Everyone, this is Austin. He will be giving us an overview of next week's experiment, the Clapeyron experiment.
Yeah, like I said, I'm going to give an overview of the Clapeyron experiment from Monfrey. This quick overview of my presentation. We're going to go over the definition of the equation, the theory, and kind of derivation of it, the objective of our experiment, the overall apparatus and overview of the equipment that we have. Then we'll look at comparing saturated pressures and temperatures, and look at some sample calcs comparing the steam tables, and then we'll wrap it up with what we expect to get from this experiment. So like you probably said, what the hell is the Clapeyron equation? So that's one of the inventors. There's two, him and Clausius. So pretty much just relates saturated pressure and temperature to enthalpy and through the phase change, as well as the specific volume of that phase change. So for an example, you'll be able to get enthalpy that isn't a measurable value from knowing the saturated pressure as well as the temperature of that liquid. And this is the Clapeyron equation at the bottom of the screen. So first, for derivation of theory, we have to know the first and second law of thermodynamics and kind of bring back Carnot cycle. So we'll consider that. We know from Carnot cycle that heat was equal to mass times the entropy. From there, we'll take the efficiency of the Carnot cycle, which is work over heat, which we can then write as heat in minus heat out over heat in, which then can simplify to temperature, the hot temperature minus the cold temperature over the hot, which then we simplify that to just dW over Q is equal to dt over T. And then we know from a Carnot cycle that the work is mass times specific volume times the pressure, change pressure. So now we're going to take all four of these equations and kind of put them into one, plugging in dW and dt and Q and equaling it to dt. And then just kind of reworking it, we can get the Clapeyron equations right here. You can also use the ideal gas law for this, only if the specific volume of the fluid is less than the gas. So then you just substitute RT over Pn, and you'll get this form of the Clapeyron equation. From there, we're going to move into our objective of our experiment. So our objective is to determine the latent heat, so the enthalpy of the evaporation of water from certain set pressures and temperatures that we'll control. And then from there, we'll verify our enthalpy that we calculate to the steam tables. For now, I want to look at the apparatus, kind of the overview of what the experiment holds. If you look on the left, they have the data, which will have software that will take the readings from the transducer and the thermocouple. The thermocouple is going to be actually inside of the beaker, taking the temperature of the waters, and the transducer is going to kind of be out, measuring the pressures of the beaker. The hot plate is going to be used to control our temperatures, and then if you look to the right, we have a pump and a water reservoir that's going to cycle, that creates a vacuum that traps a vapor flow and blows it out of the beaker. So here I have a saturated pressure versus temperature graph that I just went into an old thermo book and plotted the saturated pressures and temperatures. If you look from between 100 to 150, the pressures don't change much, but once you get to 200 to, I think the max is 350, 355 that it goes to, the pressure begins to jump as the temperature gets extremely high, by thousands. So now we're going to compare just arbitrary pressures to the actual steam table value using the Clapeyron equation. If you look at the top, we're just going to be using dP over dt equals enthalpy times pressure over temperature squared times the gas constant. So I took pressure 1 at 12.352 just because it was simple. I could just go get the enthalpy from the table, which you can see is off by like 20, which is extremely close. Same with the pressure of 476. They were off by maybe 100, which is close as well, but once I got to the extremely high pressures, it was off by 1,000, which I guess once it gets really high, the equation gets unstable. So for the expectations of this experiment, we'll have to kind of plot what I just showed, but with our own data. So I expect that our data will be very similar with the trend and the overall of what I just showed you. So we'll kind of follow that same curve, get the same pressures for temperatures, and get the same LLP. But for procedure 1, we have to do the same thing again, but I believe we're going to have a high amount of error since we're taking the local derivative, and that's just simply because we have high error that comes with localized derivatives. And then for procedure 2 and 3, I believe that we're going to get extremely close to the actual data because we are correcting that localized derivative by just simply writing a equation for pressures and temperatures, which will eliminate that error. Any questions?